Alright, the long-awaited 4.6 video is finally out. It's going to be dealing with related rates of change. What our objectives are in this chapter are to review some formulas that we have, which again are just going to be equations that link or relate to different variables. For example, area would link to radius for a circle, so we have a formula for that. Therefore, when we derive these formulas, what we're going to be doing is seeing the relationship between rates of changes, so of these variables. So that's what we're doing in this 4.6. So here are some formulas. All of these are in the front page of your textbook, so you can look at them there. I do have one quick modification to this one. So for the cone, volume of a cone would be V equals, and then we have pi r squared h over 3. It's the area of a circle, so that's what that a was here, and then to the times the height times 1/3. So if you had a cone, this is what we would use. Alright, you are not expected to memorize these, but if you know them, that's the better off you'll be. So here are the steps, and we'll do an example with this. The steps to find these related rates, or to solve these related rates of change problems, are down below. What you always want to be able to do is draw a diagram if possible. Alright, so I'm going to go ahead and write these down and pause me if you want, but I'm going to just dive right into this problem. This example is the example 2 on page 301, and we're going to step right through it using our steps to related rate of change problems. So a pebble is dropped into a calm pond, causing ripples to form in circles. I'm going to draw my pebble. And when it hits the pond, it's going to have these rings, right? So here's my rings. These are ripples in the water. Okay, so the radius of the outer ripple is increasing at a constant rate of 1 foot per second. So I'm just going to say, I'm going to draw an arrow going this way, and the outer ripple, we're talking the radius, so I'm going to talk this radius here. It's a rate of change, so I'm going to be so bold as to say dr dt is equal to 1 foot per second. Okay, so the rate of change of our r with this time is 1 foot per second, and it makes sense that it looks like a speed because we're talking a derivative here, an instantaneous rate of change, which is also an instantaneous velocity in a lot of cases. So when the radius is 3 feet, so radius is at 3 feet, we're trying to say what is the total, at what rate is the total area of the disturbed water changing. So we're trying to find the rate of change of A. So I just kind of went through that kind of quickly. So if you want to, go back and kind of see, here's my drawing, here's what's happening, and here are some labels that I was able to identify as I read along. So I just drew a diagram, and I started to identify given information indicating things with rates of change as derivative. That's what I did in step 2. Pause me if you're not sure what the heck I just did there. Okay? Write an equation relating quantities. If necessary, use geometry to eliminate one variable by substitution. Alright, so I'm going to say that we have area. We're talking circles here, so what we're going to want to use is go back to the formulas that you have, that we are going to come up with an area equals pi r squared. That right there is an area, or is a formula that will link a radius to an area of a circle, and that's what I have going on here. So we are going to be then use the chain rule to differentiate both sides of the equation with respect to time. Normally we have been deriving with respect to x. Now I'm going to go with respect to t, because I want a derivative to be with respect to time. So here I'm going to say, well, let's go ahead and derive. So d dt of the area, what's the rate of change with respect to time of the area, to d dt of pi r squared. Okay, since that's what it's equal to. So dA dt is equal to, I'm going to pull out my pi. So now what I have is this r squared, which would overall be the power rule, except for, careful, what we had with the implicit differentiation, our variables do not match up. So we don't know what radius is with respect to time, so therefore we can only assume that this is some sort of inner function. This is going to be our chain rule. So we have dA dt equals, and then pi is just a scalar multiple, so we're going to kind of ignore that for now. We're going to drive this, so we're going to get 2r to the first, right, because I pulled down the 1, or the 2, and I reduced the 2 by 1, and then times dr dt. So what we have here, and then if we go ahead and simplify this all out, we have 2 pi r times dr dt. Again, what these related rates of change problems are, going from the review of using formulas that relates two variables together, and then when we drive them, now we have two rates of changes that are linked together in a relationship. Clearly, as these circles increase in size with the radius, clearly there's a rate of change going on with the area as well. So that's what we have in the end. So now we have to revisit, substitute given information into the resulting equations to solve the unknown. So we had my radius. I'm going to go ahead and put that in. So I don't know my dA dt. I did know my dr dt. So dA dt is equal to 2 times pi times 3, gotten from this, times 1. So the rate of change at which the area is changing at that instantaneous moment of 3 feet, because that's when they were interested in, at 3 feet, what was that instantaneous rate of change of the area? Well, it was 6 pi. And you could leave it like that, otherwise you could take that 6 times 3.14. So nice short problem, or nice short video, right? These are going to be the problems. We'll start chipping away with those in class together. You're going to probably be screaming for some more examples. Here are some good YouTube videos to watch as well.